Yeah, okay, so I'm gonna start. Yeah, so my talk will be about, like the title of my talk is Models and Your Own Model. And what I'm gonna do is I'm just gonna show how to implement one specific model, which is a model where Dirac fermions are coupled to Ising models. So I'm actually, there will be no perfect squares in this model, but only fermions coupled to Ising spins. So yeah, first some, so to say, motivation or teaser or whatever, a little bit of physics before we go into the ALF specifics. Namely, so the model I'm going to present is basically the results from this model is to be found in this preprint with the title Nematic Quantum Criticality in Dirac Systems. And what this model does is it shows a nematic phase transition of Dirac fermions. So basically, like Dirac fermions, you're probably familiar with fermions with this linear dispersions on this nodal points. And what they do, what this model does, it spontaneously breaks the rotation symmetry and allows the meandering of Dirac cones, but this is then so-called this is then called a nematic phase transition, and it's a quantum phase transition. And we found a continuous transition, actually not only in this model, but also in another model without emergent Lorentz symmetry, which is like most critical points have a emergent Lorentz symmetry. This one does not. And what's very like one could say special about this point is that it has a very slow RG flow, and therefore our numerical and probably also experimental results will not probe the infrared fixed points of the RG flow. And there's also this model, this phase transition also follows the concept of a quasi-universality, where we don't really have universality because we're not at the fixed point, but we're pretty close because it's only the behavior only depends on a small number of macroscopic quantities or microscopic quantities. And yeah, now first step, I'm gonna briefly introduce the basic layout of the model. So it has three parts. First, non-interacting Dirac fermions, which are this fermions on a pi flux square lattice. It's a little bit different from the one Farka mentioned yesterday. It has a different gauge where like basically all bonds have a e to the I pi quarter phase. So it's more like more spread out this pi phase. Then the second part is a transverse field Ising model, as probably most people know, with the nearest neighbors Ising spin interaction and the transverse field, which makes the model quantum, and then what one can call a Yukawa type interaction, which is a hopping or which are fermionic hoppings that get modulated by the rotation of the spin, and each spin modulates 4 different hopping amplitudes. And the connection to ALF is here. So this part you've probably seen a few times, which is the basically describes all the Hamiltonian, which can be simulated with ALF. And what if we want to identify this Hamiltonian with this one, then we'll see that H0 is this kinetic part. We don't have a perfect square part in our model. The Yukawa coupling is this HI, And the easing action will be represented by this basically free bosonic part one has to manually define and give to ALF. So, and now the steps for writing a new Hamiltonian from scratch are to create this Hamiltonian file. I'm going to call this the Hamiltonian nematic _ Dirac. And we have to create this file in proc Hamiltonians, and then go through a few steps, define the parameters of the model, create the lattice, the hopping, and the interaction. And part of the interaction will also be defining the dynamics of the bosonic Ising field. And finally also define some observables that we also measure some stuff. And when we have this Hamiltonian, we also have to just add this nematic Dirac to this proc Hamiltonians.list file that the compiler knows it has to take care of this one, basically. Yeah, and so now I'm going to do this step by step, and I really try to basically do it from scratch, or more or less from not really from scratch, but I'm gonna copying from a cheat sheet all the stuff, and I'm gonna really start from this template we have provided. And yeah, so, and now I'm gonna open this template. And the first step is replace all occurrences of name with nematic Dirac. So as most editors have a nice feature to replace the stuff, and I'm gonna go through here. First, the name of the submodule has to change. So yeah, this actually I should change to a, if I really wanted to do this description should say something about the model. But yeah, here again, the name of the submodule, then the name of the Hamiltonian object is this. I'm also going to change. Then the name of the function which will allocate our Hamiltonian. So this is basically the mechanic which will choose one of the Hamiltonians, and if this is called, this Hamiltonians will be chosen as the Hamiltonian that gets simulated by ALF. Then next, there's a automatically generated file that that is generated from the parameter list that does the reading and writing of the parameters for you. And yeah, I'm just gonna go through this, and then yeah, this is already done now. So now the first step is, as I mentioned earlier, defining the parameters. So yeah, if the font is too small, you should someone should speak up. So yeah, if things can't be read, yeah, okay, but it seems to be fine so far. So here's basically the start of a template for defining the parameters, and it works like that. Basically one can define multiple parameter lists, which ALF will then create for you so-called name list, which is a Fortran structure. I'm just going to copy from my cheat sheet the way I want to have it, like the way the parameter list I want to have. Each parameter list has to start with this with such a parameter start and end with a parameter end. And after, in the same line as the parameter start, has to be the name of the name list. Since we added, one thing I want to mention is that Fortran is not case sensitive, so it doesn't matter if I write like dtau like this or dtau with a big T. And so you will see in the coming minutes, you will, for example, see a lot of I's, some of them small, some of them big, but it doesn't matter whether they're written capitalized or not capitalized. That's yeah. And yeah, so we have to, in this parameter list, we have to have one line per parameter. And after the parameter, we can have a comment that will also get passed and saved as a description of this parameter. Now that this is done, ALF also provides, like, this is the parsing script that tests that also automatically passes the parameters and creates this file which automatically takes care of reading in the parameters. And we can also, with this parse ham, like this is also this help option, and with the option test file, we can see whether our specifications of the parameter are correct. So we just call this, execute this script with the flag -- test file, and then the Hamiltonian we want to test, and then it will echo what it found as the parameters, and we will see that the name of the name list is var nematic Dirac, and then we have the different parameters with their default values, and with also all of them have a comment. Also, one thing I almost forgot is I have here this NSUN commented out. I have it commented out because it's already defined here in this Hamiltonian main we already also saw a few times. So, and I still want to read this NSUN in this parameter list, but I already have it defined in the Hamiltonian main. Therefore, I comment it out, and the parser will still see, okay, I will read this in this parameter list, but it's not like defined it at this point, it's declared here. Yeah. And okay, so now since we have this, we are done with this, then it's not strictly necessary, but it's really convenient to write out the parameters of the simulation in this plain text info file, which also gives, for example, information about the stabilization. And I also prepared something here, which I can just copy paste. And like this line was already present in our template, which opens this info file. And with these commands, then we can write some lines in this info file, and it will be closed again. And then we can see in our info file which parameters we used for our for this run. Then yeah, of course, here the read parameters. So this this file gets automatically generated from this list we just created. What we still have to add this call to our ham set routine. Like this is the routine where all the Hamiltonian basically gets defined, and apart from this given stuff, which is basically always the same in this Hem set. We start with a call to this read parameters function, and then the parameters get read in without having to do much on the user side. And then the next step is there are some parameters which are needed by the ALF core, which are like declared here in the Hamiltonian main, but we don't really change, or we don't really want to like give access to from outside, because it doesn't make sense to change them, or we don't want to implement the functionality for these parameters. And I just set them here as constants. Here is, for example, the number of flavors. This is basically a feature for having log diagonal elements in the Hamiltonian, and I just want one of these blocks in the Hamiltonian. Then the L trot, so the number of time slices, which is just the beta divided by d tau. I don't want to, I'm not going to implement any projector feature, which we've heard about today. So I'm gonna set it false. The theta trot is also the number of projector time slices. I'm also going to set to 0. And I'm also not going to do any symmetrization of the trotter of the operators. Then this is basically this part, which is here suggested to look like this, but as I said, I don't want to have any projector. And then the next step is to define the lattice, which is suggested to do in a separate subroutine, which I'm also going to do. So I'm again copying from my prepared stuff. Where am I? Here, this function subroutine hemlagt, to be more precise, and I'm gonna add it here right after the hem set. So this subroutine hemlet, which does a bunch of stuff. So first of all, perhaps a good time to tell a bit about how things in Fortran work. So it usually makes sense to make at the very top of a subroutine or function or anything this statement implicit none, which basically says I'm not going to assume the values of any variables. Any variables I have to work, the compiler has to work with, have to be declared explicitly. So this is basically like
the types. Rather the types than the values.
Yeah, the types. Any variable. Yeah. So for example, if I don't have implicit none, I don't have to declare this I, because the compiler will assume that if I use I anywhere, that it will be an integer. And that way I have to declare everything explicitly, which is more safe. The Fortran way to do things. Yeah, and here then I'm declaring a few variables. For example, the A1 and A2 vectors, which define the probabilities, and the L1 and L2, which also define the probabilities, which are the periodic boundary condition. Yeah, Andreas, you have a question?
Yeah, I was sorry. I'm falling a little bit behind because I want to reproduce your.
Yeah, I think it makes more
whatever.
sense.
I mean, that's my problem. But I have a question related to this writing of attributes. Since so the attributes of the Hamiltonian, so the couplings basically.
The parameters and so yeah.
Yeah. So since you are using a name list to define them, could you not just iterate over the name list in order to write all that, such that the user doesn't need to define this?
That's not really how Fortran works, as far as I know. Like, I'm not sure Fortran enables iterating over a name list.
Is precisely the point where you can do it in Fortran.
Okay.
But I'm also not an expert, so I leave it to you guys to answer that question precisely.
Yeah,
but I remember from my time using Fortran that I was getting around this issue by using a name list.
Yeah, there are also a lot of non-standard things, and we try to keep to standard. So I'm not sure what's exactly the case here. I also thought about like this this feature where this read parameters file is generated automatically. It also takes care of MPI communication and things like that.
Okay.
That this is automatically included in there, but I wanted to keep it up to the user what to write to the info file, for example. Yeah.
Okay.
Like some other infos.
I see.
People would like perhaps to add there, which are kind of are derived from the steps of creating the Hamiltonian, perhaps.
Okay.
And yeah, the way it's designed right now, the user doesn't really have access to the name list because it's in this subroutine, which is generated automatically at compile time.
Okay.
Yeah, where was I? Yes, at the Hamlet. So here we have the vectors, or declared the vectors, defining the lattice, and now we first set actually two unit cells, because we have the unit cell for the fermions and the unit cells for the Ising spins. The unit cell for the fermions has two orbitals at place 0, 0 and at place 0, 1. And the Ising spins just have one orbital at 0, 0 then. And then we created Bravais lattice. We set A1 to 1, 1 and A2 to 1, -1, and set L1, the vector L1 equals to the parameter L1 times A1, and the same for L2, and then just create this lattice. Also, what I will have to add is I have to add this let unit Ising to the private variables of the Hamiltonian. So what's in the template already defined is the one let unit, but I have two unit cells, one unit cells of the fermions, and I added another unit cell type for the Ising spins. And yeah, and the last step is defining this list and inf list to communicate, to keep track of the orbital and lattice structure of the fermions, the way I already also talked about in my talk about the lattices. So I have this NC index which goes over all fermions, and the I index goes over the unit cells, and the NO goes over the orbitals per unit cell. And then from list, I can go from this index which goes over all fermions back to unit cell and orbital. And with inf list, I can get from unit cell and orbital back to this index which goes to over all fermions. So now that we have taken care of the lattice, next step is defining the hopping. So the kinetic part, which is this Pyfax square lattice. And this looks like this. Almost. No. So again, implicit none and some variables. And
sorry to interrupt,
yeah,
but as you're going out of scope, just to be clear here for me, because I'm a bit slow. So this NN list function, when I now use it, it will not return to me the nearest neighbor of the A site with respect to the B sublattice, but it will just return to me the nearest neighboring A site.
Yeah.
Okay.
Yeah. This will actually be exactly the topic of this, the content of this subroutine.
Sorry. Yes. Okay, then never mind.
So yeah, exactly. So so we now want to reproduce or write this Hamiltonian in ALF. So what we first what we have is like what we want, the object we want to write the hopping into is this OPT, which is one of the variables defined in the Hamilton main mod. And so we have to first allocate it, and the first index is the number of checkerboard elements. I don't want to do a checkerboard decomposition, so I'm just going to do here 1. The second index is the number of flavors. As you saw earlier, I set NFL to 1, so I could also write here 1, but just because like to keep a bit of generality, we can keep it here. We keep this here to NFL, the number of flavors. And then the first step for creating an operator is to call this opmake with the operator we want to create, basically, and then the size of the operator. In this case, we want to go over all fermions, and so I put here ndim, which I set earlier here, which ndim is the total number of fermions, which is the size of the Poirier lattice, and the number of orbitals in the unit cell. This is actually important because it has to be set for the Monte Carlo core, because from this number, the Monte Carlo knows how big the Green's function is. And yeah, so this allocates the O and the P matrices in this object. And what we do now is we populate this O and P matrices of this operator. So yeah, so we pretty much can reproduce this what's written here on the left side 1-to-1. So the first loop is over all the unit cells, which is this sum, and then this sum over sigma is built in. So we'll ignore this basically here. This is the NSUN symmetry, which is automatically built in. As Farka also mentioned, we get the NSUN for free in ALF. And then we iterate over the 4 bonds. And so the first bond is then basically, so we first we set with this inf list, we say we have the index, the the ith unit cell, and we want to have the A side of the ith unit cell, and the A side of the ith unit cell is the orbital number 1. Also, one thing about Fortran is that if you haven't realized by now, arrays start at 1, which is, I mean, most programming languages array start at 0, but here it starts 1. So here the 1 is the A sublattice orbital 1. So this is basically this AR. And then we go here to the let NN list 0, 0. So this is just an identity. So, and here orbital 2. So this is orbital 2 means B. So this is BR, this one. And we set our hopping to, this is 1 minus E over square root of 2, which is the same as E to the I pi quarter. And this is the, this hopping strength. And now we set just I1 J1 to this value, and the inverse, or like the transpose of this to the conjugate because of this Hermitian conjugate. And the same way, like over the other 3 terms, we go analogous. So here we say we go to R plus E minus, which is actually called A2 here. This is a bit of an inconsistency, but E minus is A2. So this is this. And we want to go to the B sublattice. So we take orbital index 2. And if you have a question, just speak up. Otherwise, there's a risk I will always over.
Yes, I was just waiting until you finish the 4 terms, because the question is where is actually the sum over sigma?
The sum over sigma is built in. It's
sorry.
It's like
yeah, you mentioned
NSUN we get for free by.
Okay.
It's basically just a power of the action, which is computed in the core. Like you, in the end, to get this NSUN. This.
Okay.
Yeah,
and this
it's basically just.
So this NFL is not the number of sigma values that you have?
Come again?
The NFL number.
No, the NFL is another, like the N sigma is basically a number of fermion flavors that are independent of the matrix elements of the hoppings. Like this is not so obvious here, but like here the sigma only the sigma index only enters in these operators. So these matrix elements, if we would write this as a matrix, then the matrix elements of this of these operators are not dependent on sigma.
Yes.
And this this then one can show that this implies an SUN symmetry, and also the action factorizes just to a power to n SUN. Like if you.
Okay, but then you still allocate all these objects, right? So in this line, allocate opt 1 NFL, you still allocate all of them.
Yeah, NFL is 1. This is, and NFL is the number of block diagonal elements. So
okay,
that's another, like if we go, this perhaps makes it more clear. So like here you can see the N all.
Okay, sorry, yes. Now it's
or the sigma enters only here.
Yes.
And the S enters as a superscript of this matrix, but not as a as an index of this matrix. And so these are basically, we have NFL.
Okay.
You can have NFL blocks of this matrix, and I only have one of these blocks.
Okay. No, now it's crystal clear. Thanks.
And yeah. So yeah, we do this with all with all four of these terms, and then we actually also have to say that OIJ is because the construction also allows like a sparse construction. In this case, the O goes over all fermions, but I still have to tell it this with this this P actually says what the OI says, where the OI, so to which fermion the P makes the connection between the fermions. And there I say just P of I is I, and therefore this projector is just the identity. And I also can add some chemical potential, some doping. This model is actually doesn't have a sign problem under doping. So I could also dope the model without a sign problem. And here I also, as a prefactor of the operator, I add the delta tau. And there's also this offset. I can give the operator which I set to 0. And at the end, what's also very important is this OP set, where some matrices are calculated in the background to optimize the calculation later on in this. Yeah, one shouldn't forget this. Otherwise, there's a runtime error and people.
Before you continue, I have one very peaky and very annoying question, but to be crystal clear, that if NF is not equal to 1, such that this T matrix can have something, I mean, here it's diagonal, so it's clear. And NFL is equal to 1. But say you would have 2 flavors and a diagonal hopping matrix, then this allocate line 302, should it not be opt NFL NFL, because it should allocate a matrix of dimension NFL NFL, or?
No, this is I mean, this is just the index of this matrix. This is like which matrix I'm allocating. So this is like if NFL,
that's, I mean,
if NFL would be 2, I could do something like this.
I mean, the line above, so in 302.
No, the first index is another index. That's the, for example, the number of check. This is actually for the checkerboard decomposition. So this is should be this index, yeah.
Okay, and now to conclude, in order to make this general for NFL not equal to 1, I should loop also over small nf from 1 to NFL. Yeah. And then how would I set the elements in 322 and 23? Would it be opt 1 and small nf then, or?
Yeah, for example. Yeah.
Okay. Okay, thanks.
So let's go to the next step, the interaction. So yeah, the interaction. In our case, the interaction looks actually very similar to the hopping. So we also have like it's not shown here, but we also have the same phase factors here. And now we have, but we now have for each Ising spin, like first of all, the we now have to populate the OPV, which is the interaction matrix. And now we set for each easing spin one separate OPV. And again, we have here this NFL, which is just one. And now, yeah, we iterate over the whole lattice, the whole Purell lattice, and create for each easing spin one of these operators, which has the size of 5, because it connects this fermions with these 4 fermions, or like this fermions with this, and this fermion. And so we say, okay, the OP, the P1, so the first fermion it connects to is inflist I1, which is like AR. Yeah, so 1 is sublet is A, and I is like corresponds here to the R. And then we iterate over these 4 terms, and the first term is again the BR, like orbital 2 and identity BR, and we have the same phase term as before in the kinetic part, and like this term. And then we set basically we connect now this NC plus 1, we say NC plus 1 connects to J1, so to this to BR, and the term between then so the hopping between this and this is then this term, because we set it so in our P term in this P array, and this is then this hopping here we defined here. And again here we also have the transpose with the conjugate because of the Hermitian conjugate, and the same then for the other 3 terms. And yeah, then again we set the prefactor of this operator with d tau times psi, and here we set the type to 1. So for the kinetic part, the type is not relevant. For the interaction part, the type 2, as was the discussion earlier, mentioned in the discussion earlier, the type 2 would be a perfect square. The type 1 means that this coupled to a easing type degree of freedom. And again, we have to call OP set for each of this lat n observable interactions. Yeah, and then we have to do a bit of calculations, because we have to define the easing interaction or the easing action. So this is basically a part. This is this. If we go here to the top, corresponds to this H0I, which is the user, which is a user-defined action. So as a first step, I will sketch how to go from this quantum model to some model which we can calculate in the classical computer. So what we do is we map this d-dimensional transverse easing model to a d1-dimensional classical easing model. And the first step is a Trotter decomposition, which we also saw from Emily and Johannes. So we separate the classical part, the classical easing part with this transverse field easing part. And then this reordering. So here we already split it up in this L tau, which is the number of Trotter steps with the imaginary time step, which we call d tau in ALF, and which gives this systematic error we've also seen, and then in the next step we add basically some identities between those in this product, which then turns this so these states. This is basically like a d-dimensional state, and this is a d+1 dimensional time-space state, space-time state, the state C. And we've also seen that here these SCs have lost their head because now they are already like integers basically. And now to calculate the
sorry, so this step is not clear because
it's also very very hand waving, because if I want to do it very, I mean, I just want to basically show it very.
But the trotterization is clear, that you slice it into pieces where you have phi tau. But then phi tau, it gets an additional index C or what? So this
is C is basically all the phi the phi's tau from 1 to L tau.
So they are written in the sigma z base, such that you can take out the expectation value basically.
Yeah.
Okay.
Exactly. There. Yeah. This is in the SC basis exactly. Or sigma c. Yeah. And and then one then has to calculate a bit, and then can see that this matrix term also factorizes in the real space, and it then can be written as something like gamma times the overlap between two time slices of this SCR, and yeah, that's it. I think there's actually a prefactor missing, but this prefactor, this prefactor is here. Yeah, forget it. And so this is basically then the Monte Carlo sum, the sum over the configurations, and this is the Monte Carlo action we want to introduce into ALF. And yeah, so we have to put this thing here somehow into ALF. And what ALF, so first we set up some constants. We define some constants, which is, so first is a list which we call Ising nearest neighbor list, which basically just numbers lists the nearest neighbors of the easing term. It's just out of convenience. And this dv easing tau is is basically this this term for like it's the ratio between this term and so this term if it were parallel over this term if the spins were anti-parallel. So basically, if we get a flip, the Ising spins either flip from parallel to anti-parallel or from anti-parallel to parallel, and then we get either this weight or this weight for in this tau term, and similarly in the space term we get also like 2 times delta tau times j. Yeah, this is just get stored. For this, we also have to create here the variables to really have to declare the variables to store it, and so put these variables here, and now,
sorry,
yeah,
again. So one step back. Maybe you can also just say shut up if that's not interesting. But what did you actually do to get rid of this SX operator, so this expectation value? So which identity did you use? So yeah, precisely from that slide to the next one.
Yeah, it's. I mean, basically you have to sit down and calculate. So first of all, this factorizes into like in R. So you basically just have to calculate SC times exponential of SX,
okay.
and then you can do a Taylor expansion or anything you want, and then.
Okay, so the odd orders, they all vanish because the states will be orthogonal in SC basis, right? Because you flip it once with SX operator, so all they are orthogonal, they will drop out. Okay.
Yeah, I can't tell you spontaneously, but I mean, you just if you write it down, you will see pretty quickly what comes out.
Okay.
Yeah, in the end, you will get this tanh here.
Basically, just the matrix element of e to the sigma z x. It's just the matrix elements in the z basis of e to the sigma x.
Yeah. So and now to communicate to ALF this the Ising action, here is this function, which also has to be, so this is one of these functions here. So we have to overload it here at the beginning, like here. So in addition to this default procedures, we add this SO function, S0 function, so that it will get used instead of this this S0 base. And yeah, and this S0 basically says if I change the nth spin or the nth auxiliary field, if it's not a type 2, and if it's a type 2, the ALF will know itself, okay, it's a perfect square. I will just do what we've seen in the last few days. And if it's a type 1, then ALF will try to flip the nth spins at the time slice nt. and say, okay, I will try to flip it to this new value. This new value is not relevant for us because we have, in this case, integer spins. So we either have 1 or -1. So if we know if it's 1 right now, ALF will propose -1, and if it's -1 right now, ALF will propose 1. And then we go first over the nearest neighbors in space, and yeah, basically like make the product over these terms, depending on whether n sigma is parallel or anti-parallel. And in a similar case, we will also do this in imaginary time. Yeah, we'll just have to take care that if we are at the end at L trot, we will have to take the periodic boundary conditions and say that the time slice +1 is actually 1, and the same is also true if we are at the beginning of the like if we are at nt equals 1, then we have to make the neighbor, the time neighbor is then L trot. And yeah, that's it. And that way we can then simulate, for example, an Ising model in ALF. If we want to do single spin flips, if we want to do global updates, we also have to communicate ALF what to do in case in case more than one spin changes. And this function, I won't go over this in detail, but basically what ALF does is it basically proposes a change, or like if it's a normal global update, you actually have to also write a function to propose this change. And ALF will save the old. So this is the whole auxiliary field configuration. This will be saved, and you already have you already have access within the Hamiltonian with the new, and like the n sigma is the new n sigma, and then you will just basically with this with the equations on the left hand side, you can then calculate the difference between the difference in action between the old and the new configuration. Yeah. And yeah,
Can I ask a question real quick?
Yeah, sure.
Yeah. So this is for single spin flips, for single Ising spins?
This is for single spin flips. Yeah.
Okay, so then, okay, yeah, never mind. I was looking at the wrong function. I was confused as to why you summed over all the lattice sites. But then,
yeah, this
I was just confused.
This is in case I do global updates, or parallel tempering also uses this, which is basically also global updates. Yeah.
Okay, thanks.
And then, yeah, here one has to, like, now that basically the Hamiltonian is complete, the next step is to define the observables. Yeah, the first step is write this subroutine, which is called alloc ops, which is, I think, pretty straightforward to understand or to follow. You just have to first allocate. So there are this vectors of this obscale. Yeah, this vector called obscale, which is a vector of scalar type observables, and then you will just give the names and call this observer name and say also one of these can have multiple observables. For example, here we have 3 values in one, and then give it a name, and then it's created. Similar, it's also with lattice type observables, which are used for correlations. So you give it the observable, then the number of time steps. So for equal time observables, this is set to 1, then the name. Then you have to give it the Poiret lattice, and then the unit cell. So here I have some correlation function in the Ising degrees of freedoms, which I give the lat unit Ising or lat unit Ising, and here I have some in the in the fermion degree of freedom, which I give the lat unit. And then there's also the channel, which is relevant for the max end, which are actually, in this case, I've just set in every case to dash. So with basically to 0. And then you also have to say the imaginary time step. Yeah, that's it. Here's also I have of the ops EQ. These are actually time displaced observables, but I've because I said, okay, the number of time steps is L short plus 1. This is the size of a time displaced observable. But I've declared it as a member of the ops EQ, because these are in the Ising degrees of freedom, and in the Ising degrees of freedom, I always have access to the whole time space configuration. So I don't need to use this for if I need time displaced observables in the fermionic degrees of freedom. I always need to do extra sweeps with a frozen configuration, and this is not the case for Ising degrees of freedom. That's why I've declared this time displaced Ising variables as equal time observables, because I don't need this set to L tau to 1 if I want to only have these as time displaced observables. Yeah, and here's some time displaced observables, the Green function and the density correlations. And then yeah, the next in the next part, we will actually have to calculate these observables. And yeah, I'm not sure how I'm doing on time, how much time, because I think I'm quite over time, and if I should wrap it up or speed it up a bit.
I think you still have some time. You still have
okay. Okay.
Let's say, actually, let me. So yes, you actually are over time. Yeah. You are over time already. So you should try to wrap, not immediately, but you should try to go faster at least.
Okay, yeah. So now for the observables, I first have defined a helper function, which basically just takes the Green's function and then calculates with opt. So this is a pretty straightforward loop over opt in the Green's function, which calculates the kinetic energy. And then for the observables, so this part is default, which calculates like GR is C deca, which is the Green's function used internally in ALF, and GRC is C deca C, and so this is like default, and usually it gets used in the beginning of every, like, yeah, in the beginning of the observer, like the GRC gets calculated out of the GR, and this is already in this template, so we can keep it there. And now this is actually kind of the last part. So now calculating the observables. So the scalar observables have three parts which are like relevant for measuring, or which have to be accessed during measuring, which is first n, a counter of the number of measurements. So if you want to measure, you should increment this counter by 1. And also the sign, which will also have to be added up here, which is 1 if you don't have a sign problem. And then, yeah, there's a few calculations for different things. For example, here's the particle number, which we add to the obscal 1, which as we defined it here, we gave it the number part. And here's the Ising C, so the magnetization of the Ising spins. And yeah, so these things get calculated here, and you have to, like here, I loop over all scalar observables and just increment the counter by 1 and add the current sign. And so down here, I just have to add the measured value and add this sign factor. So this factor which comes from the phase for dealing with the sign problem. And yeah, this I do for different variables, like here for the particle number. Here I have one observable, so the observable number 3, which has a length of 3, and I add in the first, as the first component, I put the kinetic energy. As the second component, I put the potential energy, and then as the third, I put the sum over both. And yeah, do the same for a few other observables. And finally, last interesting part is the correlation functions, which have also the number and the sign, which I add here for the first two correlation functions. Like these are the XXX and the CC correlation functions. And for these, earlier in the alloc ops, I have defined these two variables, which is so this is the x. So the x value always has to be basically measured as a value between two different time slices. And so if the two different time slices, the Ising x value, if the two spins on different time slices are the same, the Ising x value is this, the tanh of d tau times h, and if they are anti-parallel, it's the reciprocal value. Actually, I also have to add it up here. This variable, declare it. And I also have something else, which I will get to in a second. Yeah, I'm sorry for going over time, but yeah.
There were many questions also. So.
Yeah. So so where was I? At this correlation functions. And here I iterate over I and over j, which both go over the whole lattice, over the whole Bravais lattice. And since we only have one orbital for the easing spins, that's enough. So we don't have to consider any orbital degrees of freedom. And then we add here up the background of the C, the X part, like which is either this EQX or NEQX for the time slice n tau and n tau plus 1. And yeah, this is this background part here. So here the number of orbitals is just, I just put it to 1 because I only have one orbital, or like the orbital index is it. And for SC, I don't like, I would have to add up this, but I say since SC to minus SC is an exact symmetry of the model, I just say, okay, I'm employing an improved estimator, it's called, where I just say SC is equal to 0, and I just set this background value to 0. And yeah, then I have to add up here the this correlation functions. So yeah, IMJ is basically the index corresponding to the difference between I and J. And yeah, so this and this are the same, and I have to increment this by the correlation of the C spins, and also always don't forget this part for the phase part, and then similar for the correlations in the C component. So I'll take from the ith spin, I take this value, and from the J spin, either if they're like the n tau and n tau plus 1 are parallel, I either take this value, or if they're anti-parallel, I take this value. And these are how the correlation functions are computed. For the green for the green function and for the density correlations, I take this predefined observables. There's one caveat. Is this loop like this summarization, this incrementation by 1, and this adding up the sign is already taken care of in this predefined function. So I do this, make this loop only until like over these two observables and not over the whole observables. Yeah, and here analogous, as I said, I can measure the time displaced easing degree of freedoms within this within the equal time observable function or subroutine. Just one thing I do here is every time this function gets calculated, I increment by 1, and I only measure this every L shorter times this observer gets called. Otherwise, like I do here, I do here measure these correlations each time over the whole over all time slices, and it's just overhead that doesn't give any added precision. So I'll just measure only every L shorter time slices this time displaced correlations. Yeah, and that's basically it. I also measure some time displaced correlations, but for these I just use the predefined structures. So this is really actually now these obsolete is doubly here. So I just copy here in this template just these two predefined subroutines. And now if people are still here and interested, this Hamiltonian should be finished. There's just one last step. I have this here Hamiltonians.list. I have to add here nematic hierarch, and now it should work. So I just first have to source the configure script. I use the GNU compiler without MPI with HDF5, and first make clean because I don't know how I compiled before, and then make program because I don't want to. I would just want to compile the program, and if it does just make it compiles everything, which includes the analysis, which I'm not interested about. So this just takes a minute, and then if everything works, let's see. I can do in parallel already prepare for testing PyAlf. So let's see if it's moment. Something I probably forgot to. Oh, yeah, that's quickly taken care of because yeah, these are just some
Jonas, is there some remark you want to make?
Yeah, yeah, I declared here this with this the type of this as DP, which in some other modules I defined this as kind of a double, but yeah, here I have to define it like that.
Mm-hmm.
And then
I think we should better not wait for the compilation and then.
Yeah, so basically I'm finished. I just have to fix probably some yeah, there are some typos right now, but basically now we're done. Yeah.
Okay, thank you very, very much. That was I'm sure that it was very illuminating for many people, and I think the recording could be stopped now, and then we could have our questions.
Thank you very much. Yes.
Sorry for the overtime.
No worries, no worries.
But I guess at least some people learned something if they were.
Yes, I mean it also started a bit later. I mean we had two. Yeah.
But it's extremely useful to have somebody doing, you know, things online. I would think. I don't know what you guys think, but thank you very much for taking the time doing this. Also, I'll stop the video.
Yeah.
And